The topic for today's lesson is Lewis structure and molecular geometry and everything that will go along with that. We're not going to finish today, but we will do a good starting position. How do you do Lewis structure, aka electron dot structure? Nowadays, sometimes they're called the Lewis dot structure. They all mean the same thing. So let me start from the beginning, in the middle. So here, when you do Lewis structure, you only work with the valence electrons. The atom in the middle, called the central atom, can never be H. H will always be a side atom. The central atom is the one that is of larger size and often less electronegative atoms. So it's up here. But otherwise, H can never be the central atom. In most cases, atoms in the molecule in a Lewis structure must follow octet rule, meaning 8 electrons have to surround each atoms. They must also follow what's called a duet rule, meaning all the electrons should be paired up. Lots of exceptions. So one exception to the duet rule would be when you have a species called radicals. When you have radicals, you would know you have a radical. When you add up all the total valence electrons, you end up with odd number. Then you know that one electron would not be paired up. So when you have a radical, that is an extremely reactive species. Okay, I think that's important for you to know. The elements in group 1, 2, and 13, for example, would not follow octet rule because, take a look at these examples. Lithium, magnesium, boron in groups 1, 2, and 13 respectively. The lithium only would have one valence electron. At the most, it can be surrounded by 2 once that electron pairs up. Magnesium would have 2 valence electrons. So when they pair up, at the most, magnesium would be surrounded by 4 electrons. Similarly, for boron, it's got 3 valence electrons. When they all pair up, at the most, the boron would be surrounded by 6 valence electrons, not 8. So there are lots of exceptions. There are other exceptions as well, like nonmetals, particularly in groups I'm thinking of 5, 6, and maybe 7s, and they're kind of obvious. Not groups, periods. Okay, periods of like 5, 6, and 7s, like P, S, Cl, Xc in the middle, being a central atom. They can have what's called expanded octet. Okay, they can have expanded octet, meaning they can be surrounded by more than 8 valence electrons. So these would be the ones with 5 domains and 6 domains. And we'll get to the meaning of domains in just a moment. Take a look at the bottom of the page. So let's see what these exception to the octet rule will look like. So when you have BH3, okay, so there would be one of the exceptions to the octet rule, and it will look like this. So let's talk about what we mean by domains. So when I say domains, it means all the regions, which also groups of electrons around the central atom that's either bonded or non-bonded. You add them up together. So any regions or groups of electrons around the central atom, we would say they are the domains. Single bond would count as one domain. Double bond would count as one domain. Triple bond count as one domain. So looking at this guy, it would have 3 domains around the central atom boron. So here's the domain number 1, domain number 2, and domain number 3, not in any particular order. Now, it would not have any lone pair around the central atom. The lone pairs would be the pair of electrons not bonded to any other atoms. And we all know that when you have three domains and lone pair 0 in this way, it would be called trigonal planar for the molecular geometry. And the bond angle would be like 120. And we've all learned that last year. Let's look at another exception to the octet rule, PF5. So looking at PF5, P would be the central atom. That's obvious. The lone pair around the central atom. So we are particularly concerned with lone pair around the central atom. Now, these are lone pairs too. So that would be a lone pair. But right now, we're concerned about the lone pair around the central atom, 0. So whenever we have 5 domains around the central atom, lone pair around the central atom being a 0, the molecular geometry would be called trigonal bipyramidal, as we've learned last year. And the bond angle would be 180, 120, and 90. When you have fluorine like this, okay, when you have a fluorine like that, you can use the 2 dots to signify the lone pair. I'm sorry, yes, to signify the lone pair, or you can just use a dash line like that, and they will be equivalent, and AP will accept that. Let's go to next page. So when you go to next page, let's take a look at some specific resonance structures. So what do we mean by resonance structure? The resonance structure is when you have more than one valid Lewis structure. Then we call this resonance structure. And we've learned this last year as well. Example, NO3 negative 1. So you can have a double bond in NO3 negative 1 here, here, or here. 3 would be like equivalent structures. So you have to put the bracket over each one of them and put like double-headed arrows between them. And then outside the bracket, you must add the sign negative 1. So let's count up all the valence electrons. Well, 5 coming from nitrogen, 6 coming from each of the O's, but one more you have to add because of negative 1. Then you have to add one more electron. So a total of 24 valence electrons you have to work with. Dividing that by 2 to satisfy the duet rule, you have to account for 12 electron pairs. And this is just one way to keep track of all your electrons as you do Lewis structure. So if you count up all the electron pairs, you should come up with 12. In actuality, NO3 negative species does not exist like this, nor like that, nor like that. In actuality, they exist as a hybrid like that. So each bond is not a single bond. Each bond is not a double bond. They all would have one bond, but the second bond, you can think of it as being distributed over 3 bonds, giving you effectively 1.33 bond, or 1 1/3 bond. As you've learned, let me go a quick hybridization review, and I will touch upon this a little bit more detail in a few minutes. But this is what we've learned last year. Hybridization is a fancy way of saying like mixed, right? For now, think of hybridization as another label for domains, the number of domains. So if you have 2 domains, we say, oh, that's sp hybridization. 3 domains, sp2 hybridization. 4 domains, sp3 hybridization. 5 domains, sp3d or dsp3 hybridization. 6 domains, sp3d2 or d2 sp3. We always say, oh, it's the hybridization around the central atom. Okay, that is what we will be concerned with. So 2 domains, 3 domains, 4 domains, 5 domains, 6 domains, it doesn't matter how many lone pairs you would have. If you have 2, SP, 3, SP2, 4, SP3, 5, SP3D or DSP3, 6 domains, SP3D2 or D2 SP3. Again, I will touch upon just a little bit more about this in just in a few minutes. So for this, nitrogen, it's got 3 domains around the central atom. It's got 3 domains. It has no lone pair. In terms of hybridization, it would be sp2. 3 domains, sp2. And that's how everything is connected. Again, we're talking about around the central atom, in this case, that being nitrogen. Let's look at some visual of valence electrons. So group 1 would have 1 valence electron, 2 would have 2. We kind of skip over the transition metals, and then we go right to group 13 all the way to 18. So this would have 1 valence electron, 2 valence electrons. Group 13 would have 3 all the way to 8 valence electrons. And it shows you nicely how you can visualize the valence electrons. Let's go to the bottom portion of the page. So anytime you have a single bond, that would, and you just keep in mind, oh yeah, that's 2 electrons, 1 line, 2 lines, double bond, 4 electrons, triple bond, okay, that's 1, 2, 3 lines, 6 electrons. So again, here it shows you the number of valence electrons that we've just talked about. The one thing that's interesting is this guy right here that I've circled, that's helium. Helium only has 2 valence electrons, not 8 like other noble gases, because it only has 2 electrons, like that. Let's go to next page. So let's look at some examples of Lewis structures being drawn out. So here you have 1 carbon with 4 valence electrons combining with 4, 1H, and each H would have 1 valence electrons. So when they combine, they will look like this. Number two, you should have 1, 2, 3. That's the lone pair. Can you fix that? So we would have 1 electron right there and 1 pair of electron with 5 valence electrons plus H, 3 of them, each having 1 electron. And they combine to give you this structure. And that right there, you would see, is a lone pair around the central atom, The nitrogen, it's got triple bond, as you can see. And this is the only way that you can satisfy the octet rule, for example. Number 4, O2, it needs to have 2 double bonds. So again, let's practice counting up the valence electrons. So you have 6 and 6 coming from each of the oxygens, dividing that by 2 to satisfy the duad rule. You have to account for 6 electron pairs. And if you count up electron pairs, you have 6. Let's keep on going. Let's look at the rest of them. And you can look at example CO2, 2 double bonds. And if you count up all the valence electrons, you got 4 from carbon, 6 from each of the oxygens, dividing that by 2, you should have 8 electron pairs accounting for, and you do. For the SO2, it seemed like it's similar to CO2, but it's got like 1 lone pair. And because of that, it's actually a resonance structure looking like this. So you can throw in a double bond at this position or that position. So SO2 is a resonance structure. Finishing up the examples here. So we have AsBr3 arsenic tribromide. It will look like this. Again, For BR on the AP exam, you can use the dash lines like that. Each line representing 2 electrons. And in this case, Cl, you can draw Cl out like this. Next page. So here's an example of radical, which is NO2. So if you look at NO2, okay, it's a radical. You have odd number of valence electrons. It's extremely reactive. Oops, it's extremely reactive. Looking at CS2. Now CS2 is very much like CO2, right? So try to get a big picture. So when you look at CS2, and you go, oh, S is in the same group as oxygen with the same number of valence electrons. So their Lewis structure will look similar. And we've looked at O2 and N2 before. And we've looked at BF3. Okay, here's another radical. Okay, be able to recognize the radical as well. When you have odd number of valence electrons, that's a radical. The resonance structures below that page, we will be looking at that some other time. Okay, not today. Next, let's go on to looking at the molecular geometry. Oops, before we get to molecular geometry, one more. Please go to page 21. And let me talk about hybridization just a little bit on page 21. So here you have 2 domains, 3 domains, 4 domains, 5 domains, and 6 domains. So you can think of these as being domains. So when you have 2, 3, 4, 5, 6, and for now, we would say, you know what, they have no lone pairs. Okay, they have no lone pairs. Then their molecular geometry would be linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. We'll be looking at the molecular geometry in just a moment and review that. So to make a linear molecule, okay, and I'll give you one linear molecule, BeCl2. That's a linear molecule. It's got 2 domains, 0 lone pair. What happens is beryllium, Be in the middle, mixes S and P orbitals. So you take one S and one P and you mix, hybridize. So when you mix them, hybridizing, you end up getting new orbital. It's not S orbital, it's not P orbital, it's called SP orbital. And you get 2 equivalent SPs. So now that's an SP orbital that beryllium is using to make a bond. That is SP orbital being used to make a bond, 2 equivalent bonds. And 2 equivalent bonding regions would be 2 domains. That's how you would think of it as. So I would say, what's the hybridization around the beryllium? SP. Let's go on to SP2. So SP2 would be for 3 domains. Give you an example. AlCl3. And you would have 3 domains. I have no lone pair. It's a trigonal planar molecule, as you can see, with 120 bond angle. To make these 3 equivalent regions around the central atom that it can use to make bond, it needs to mix 1s with 2 p's. Oops, let me do it this way. S plus 2 p's and hybridize, meaning you mix. And when you mix, you end up with new orbital called sp2. So you have 3 sp2 bonding ability. So each of these bonds are using sp2 orbitals, 3 equivalent sp2 orbitals being used by aluminum to make 3 equivalent bonds. So we would say, what's the hybridization around the central atom aluminum? You would say sp2. And similarly, that would be true for sp3, sp3d, and sp3d2. And for sp3d, you can say dsp3. Sometimes d is mentioned first. And sp3d2 and d2sp3. To make the long story short, on the AP exam, they will focus on sp, sp2, and sp3. Okay, they used to ask students about these, but the emphasis is kind of gone. So on the AP exam, make sure you know SP, SP2, and SP3. I will ask you about these on my exam, but I think you should just know, just in case. So let's look at the actual molecular geometry. Looking at from page 10. Everyone, please go to page 10. And we've all learned this last year, so this will be a quick review. So we'll start with domains 2, 3, and 4 right there, right? And then here we have, let's change that to domain. I like to use domain with lone pair. So you would memorize it like this. 2 domains, 0 lone pair, linear. 3 domains, 0, trigonal planar. 3, 1, angular, bent, or V-shaped. 4, 0, tetrahedral. 4, 1, trigonal, pyramidal. 4, 2, angular, bent, or V-shaped. That's how I would like to memorize it. I think that's easiest. And to correspond to the number of domains, regardless of the lone pairs, 2 would be sp hybridization around the central atom. Any 3 domains would be sp2s. Any 4 domains would be of sp3s. We're not going to look at polarity now, and this we'll be looking at maybe tomorrow. So looking at the bond angles, let's look at 2, 0. It can only be 180. That's linear. Let's look at the 3, 0. Okay, so 3, 0 looks like this. Trigonal planar, meaning all the atoms lie on the same plane. That's what planar means, triangular based. And it's like equilateral triangle, and each bond right there would be 120 of a bond angle. Looking at 3, 1, it's got bent, angular, or V-shaped. So what is so interesting about this particular molecular geometry is that one of the 3 domains would be a lone pair. The lone pair seems to take up more space, and they exert greater repulsion force upon the other remaining angle. And as we all know, the bonds are made up of electrons, and they repel one another. That's why the bonds will like to be as far away from each other as possible, according to that VSEPR theory that we've learned last year. So when you have a lone pair, it seems to have greater effect of repelling the other bond. And because of that, the remaining bond gets squeezed a little bit more so. So it turns out to be less than 120 compared to 3, 0. Good number to remember, it's like 117. That would be a good number to remember. 4, 1. So for the bonds to be as far away from each other as possible, it will not be a cross, as we have seen last year. Not a cross configuration. It'll be tetrahedral. And tetrahedral would have of a configuration looking like this. So you have this bond on the plane of the paper. This bond right there is coming towards you. Sometimes it's used with elongated triangle to denote the fact that it is coming towards you. And the last bond right there, a lot of people use ... to signify the fact that that bond is going behind the plane of this paper. So with 4-0, it's called tetrahedral. When you connect all the vertices, you end up with 4 faces. Trigonal pyramidal is your 4-1 with 1 lone pair. So again, the lone pair, the bond angle for tetrahedral, 109.5. And all of us know that from last year. The trigonal pyramidal has 1 lone pair. Okay, just as it happened up here, it would exert greater repulsion force upon the remaining bond, squeezing that bond together closer, and the bond angle would be less than 109.5. 107 is a good number to remember. Now 4-2, okay, 4-2 is angular, bent, V-shaped. The molecular geometry is self-explanatory. It's got 2 lone pairs. The 2 lone pairs will exert even greater repulsion force onto the remaining bond angle. And a good number to remember is like 104. This is often a very common question on any tests. They will give you like tetrahedral, trigonal pyramidal, and then they'll give you angular bent-shaped one. And they will say rank the bond angles in terms of the size, from like largest to smallest, etc. And be able to explain involving the existence of the lone pair. Let's look at 5 domains and 6 domains. Looking at 5 domains, so you go 5, 0. It's called trigonal bipyramidal because it seems to be it seems to have that triangular base in the middle. Often that's referred to as equatorial kind of position, like around the equator, equatorial. And then you have one axial bond going up, another axial bond going down. So in terms of 3D, you can think of axial being perpendicular to the equatorial positions. And it's called trigonal bipyramidal because it's triangular based, 2 pyramids, 1 pyramid going up, 1 pyramid going down, and they're joined at the base. So it's triangular based, 2 pyramids joined at the base. 5-1 is a seesaw. The 1 lone pair. Let me quickly talk of the bond angles here before I move on. So for 5-0, the bond angles you would see would be 120 and 90. That's obvious. For 5-1, for the same because of the same reason that we've talked about, 1 lone pair will exert greater repulsive force onto the remaining bond angles. It would squeeze the bond angles closer, making that less than 120, less than 90. Now, this is called the seesaw structure. To see the seesaw structure better, I think page 19 gives you a better view of what that may look like. So let's go to page 19, which is this. Okay, if you go to page 19, this is a seesaw. So here's your equatorial position with perpendicular to the axial. If we put the lone pair right there, right, we'll make that the lone pair. And we kind of move this 90 degrees, like that, like so. You could see it's like a seesaw, like the seesaw that you would see in a playground. Okay, so I like this picture right there on page 19. So let's go back to the page that we were at, page 10. What if you have 2 lone pairs? So if you have 5-2, it's called a T-shaped because the remaining atoms seems to take up the shape of a T, the letter T. But it's not exactly T-shaped because of the 2 lone pairs. And they would repel onto the remaining bonds, squeezing them together the bond would be less than 90. 5,3 is an interesting molecule. They're all interesting, but 5,3 is kind of a particular, it's interesting in its own way. It's got 3 lone pair along the equatorial positions. So what does that mean? So each lone pairs would be repelling onto the remaining bond right there, but 3 would do so, okay, in a way that all the repulsion force will be canceled out. So you have this linear staying, remaining linear, and the bond angle of 180. And because of the molecular geometry, and that would be the reason why those effects of repulsion would all be canceled out. So bond angle 180, once again, is linear. Let's talk about 6 domains. The 6 domains, 6, 0, is called the octahedral. Okay, it will look like this. So you have square kind of in the equatorial position. You have axial, axial. The bond angle would be 90. It is called octahedral because if you were to connect all the vertices, you end up with 8 faces. 6, 1 is called square pyramidal. So let's say this here is the lone pair. And now you have square-based pyramid, with that being the apex. The bond angle, however, will be less than 90 because of the lone pair below exerting repulsion force onto the remaining bond angles. If you have 6, 2, it's called square planar, and that's obvious. You can square here in the middle. So you have lone pair up above, and you have a lone pair at below. Again, they would be repelling, they would be exerting repulsive force onto the remaining bond angles. But the effect of top and the bottom, the 2 effects will just cancel out. And the configuration will stay square planar, meaning they would all lie on the same plane, square planar. So we have 2 planar structures, and I have circled those on the paper. So here, this is also trigonal planar, and this one would be square planar. Just be aware of that.